In this lecture, we are going to look at an application of implicit differentiation, namely a set of word problems commonly referred to as related rates problems. These are the problems where solutions require finding a relation between known and unknown rates of change. The goal is to compute the rate of change of one quantity in terms of the rate of change of the other. The key is to remember that the rate of change is the derivative. Our strategy for solving a related rate problem is the following. First, read the problem. Draw a diagram and introduce the notation. Then write an equation relating the quantities of the problem. If necessary, use area or volume formulas, the Pythagorean theorem or similar triangles from geometry, or any other formulas. Differentiate your equation implicitly with respect to time. Remember to use the chain rule. In the resulting related rates equation, substitute the given numerical quantities and rates. Then solve for the unknown. There are two things to watch out for here. One is to not substitute values for the variables until after you have computed all the derivatives. The other is to remember that a rate of change of a quantity is a positive number if that quantity is increasing, and is a negative number if that quantity is decreasing. Be sure to include the appropriate units of measurement with your answer. The rest of our lecture will be spent on working 5 examples. Here is example number 1. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? The first step is to draw a diagram and choose variables for any related quantities. We draw a rectangle and denote its length by x, its width by y, and its area by a. As usual, t stands for time. In this problem, the length, width, and the area are functions of time. The rate of increase of the length x with respect to time is the derivative of x with respect to t, and here it is 8 centimeters per second. The rate of increase of the width y with respect to time is the derivative of y with respect to t, and here it is 3 centimeters per second. We need to find the rate of change of the area, dA dt, at the moment when x is 20 and y is 10. To solve the problem, we need an equation relating x, y, and a. We know that the area of a rectangle is length times width. Therefore, a is x times y. To calculate the derivative of a with respect to t, we differentiate both sides of this equation with respect to t. Using the product rule, we get dA dt equals dx dt times y plus x times dy dt. Now we substitute the given information. Dx dt is 8, y is 10, x is 20, and dy dt is 3. We get that dA dt equals 8 times 10 plus 20 times 3, which is 120. So when the length is 20 and the width is 10, the area is increasing at a rate of 120 centimeters squared per second. Let's look at another example. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? First, we draw a diagram. At noon, ship A is 150 kilometers west of ship B. We denote by T the time elapsed since noon. Ship A is sailing east. We denote by X distance traveled by A since noon. Ship B is sailing north. We denote by Y the distance traveled by B since noon. Let Z be the distance between A and B at time t. Since velocity is the rate of change of distance with respect to time, we are given that the derivative of x with respect to t is the velocity of A, which is 35 kilometers per hour, and the derivative of y with respect to t is the velocity of B, which is 25 kilometers per hour. We need to find the rate of change of the distance between ships, dz dt, at time t equals 4. We need an equation relating x, y, and z. This is provided by Pythagorean theorem from this red triangle. The hypotenuse is z, one of the sides is y, and the other side is 150 minus x. So the Pythagorean theorem gives z squared equals 150 minus x squared plus y squared. Here x, y, and z are functions of t. Let's differentiate both sides of this equation with respect to t. According to the chain rule, the derivative of z squared is 2z times dz dt. The derivative of 150 minus x squared is 2 times 150 minus x times negative dx dt. And the derivative of y squared is 2y times dy dt. From this equation, we will be able to find the derivative of z with respect to t at time t equals 4. Since ships move at a constant rate, we know that dx dt equals 35 and dy dt equals 25. However, we still need to compute the distances x, y, and z at time t equals 4. When t equals 4, ship A was sailing at 35 miles per hour for 4 hours. Thus, the distance x traveled by A is 35 times 4 equals 140 miles. Ship B was sailing at 25 miles per hour for 4 hours. Thus, the distance it covered is y equals 25 times 4 equals 100 miles. Z at time 4 is given by Pythagorean theorem. Z squared equals 150 minus 140 squared plus 100 squared equals 10,100, which gives z equals 10 square root of 101. We plug in all the quantities into the equation for the derivatives. We get 2 times 10 square root of 101 dz dt equals 2 times 150 minus 140 times negative 35 plus 2 times 100 times 25. After performing the calculations and solving for dz dt, we obtain that at 4 p.m. the distance between ships is increasing at a rate of 440 divided by square root of 101 kilometers per hour. Let's move on to our next example. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? We draw a diagram of a kite moving horizontally 100 feet above the ground. Let t be the time elapsed measured in seconds and x be the distance traveled by the kite. We denote by y the length of the string at time t and by theta the angle between the string and the horizontal. We are given that the speed of the kite, which is the rate of change of the distance it traveled, x, with respect to time, is 8 feet per second. Our goal is to find the rate of change of the angle theta at the moment when the length of the string y is 200 feet. We need a relation between the rates of change of x and theta. From the red triangle, we see that tangent theta equals 100 divided by x. Now differentiate this equation with respect to time. The derivative of tangent theta is secant squared theta times the derivative of theta with respect to t equals 100 times the derivative of 1 over x, which is negative 1 over x squared times dx dt. Now we need to use the given data to find the unknown derivative, d theta dt. We use the red triangle with y equals 200. Then by Pythagorean theorem, x squared equals 200 squared minus 100 squared equals 30,000. Also, since secant theta is y divided by x, secant squared theta is y squared divided by x squared equals 40,000 divided by 30,000 equals 4/3. Together with the fact that dx dt equals 8, we have all the necessary data to plug into the equation for the derivatives and solve for d theta dt. We get 4/3 times d theta dt equals negative 100 divided by 30,000 times 8. Dividing both sides by 4/3, we obtain that d theta dt equals negative 0.02 radians per second. Thus the angle decreases at a rate of 0.02 radians per second. Let's move on to example 4. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. How long is the ladder? Our first step, as always, is to draw a diagram and introduce the notation. We denote by x the distance of the bottom of the ladder to the wall at time t, and by y the distance of the top of the ladder to the ground at time t. Also, let L be the length of the ladder. We are given that the velocity of the top is 0.15 meters per second. This means that the derivative of y with respect to t is negative 0.15, since y is decreasing. Also, at the moment when x equals 3, the rate of change of x is 0.2 meters per second. We need to find the length of the ladder L. By Pythagorean theorem, L squared equals x squared plus y squared. If we know both x and y, we can compute L. Since x and y are changing with time, we look for a relation between their rates of change. Let's differentiate the last equation with respect to t. Since L is a constant, the derivative of L is 0. So we get 0 equals 2x times dx dt plus 2y times dy dt. We know that when x equals 3, dx dt equals 0.2 and dy dt equals negative 0.15. Let's plug in this data into our equation. We get 0 equals 2 times 3 times 0.2 plus 2y times negative 0.15. From here we get that y equals 4. Since x is 3, we obtain L squared equals 3 squared plus 4 squared equals 25. Therefore, the length of the ladder L is 5 meters. Our last example is the following problem. Water pours into a fish tank at a rate of 3 cubic feet per minute. How fast is the water level rising if the base of the tank is a rectangle of dimensions 2 by 3 feet. The picture shows the fish tank with a rectangular bottom, and we denote by h the height of the water at time t. We recognize that the rate at which the water pours into the tank is the derivative of water volume with respect to time. Therefore, let V be the volume of the water in the tank at time t. We are given that the derivative of V with respect to t is 3 cubic feet per minute. We need to find dH dt. The volume equals length times width times height. Therefore, V equals 3 times 2 times h equals 6h. Differentiating this equation with respect to t, we obtain dV dt equals 6 dH dt. We plug in 3 for dV dt. We get 3 equals 6 times dH dt. Now solving for dH dt, we get that the rate at which the water level is rising is 0.5 feet per minute. This is the end of our lecture.